Okay, let's talk about decimals and adding. We've been spending a lot of time on fractions, so let's see how these are related to decimals. Alright, there are a special class of fractions whose partition, or those with partitions and denominators of powers of 10. So here are some examples. We've been talking mostly about fractions with simple partitions, but remember that anything can be a partition, and obviously those powers of 10 like 100 or 100,000 or 10,000 could also be partitions. So you don't have to write all this down, but just some background as to where decimals came from. So these types of fractions were called decimal fractions, deci meaning 10, so powers of 10. But they're better known in a different notation under slightly different name. And this Jesuit astronomer, C. Clavius, decided, let's quit using fractions in this case and just use a decimal point. So the decimal point is based on the fact that here is 2 zeros on this one, so that's where 14.89, drop the fraction bar and just put a decimal point there. There are 5 zeros in 2400 thousandths, so let's just drop that and write this as 2400 thousandths. And the same thing here, we have 4 zeros, so we put the decimal point 4 places into the number and make it 5 and 89 10,000ths. So that's where the decimal point comes from, is just a dropping of the fraction bar. So a number expressed in this type of notation of the decimal point is called a finite or terminating decimal. Terminating means to stop, meaning it doesn't repeat, and we will talk about repeating decimals later. So the number of decimal digits, the digits to the right of the decimal point correspond with the number of zeros in the respective denominators. So again, 2 in 14.89, 5 zeros in the partition of 2400 thousandths, and 4 zeros in the partitioning of 5 and 89 10,000ths. Alright, so let's take a closer look at these. If we rewrite these above decimal fractions using exponents, then they become 1489 over 10 to the second power. And in case you've forgotten what exponent means, it means repeated multiplication. So this is 10 times 10, which of course is 100. If you take 10 times 10 5 times, not 10 times 5, that's 50, but 10 times 10 times 10 times 10, 5 times, you get 100,000. And if you're not sure, check it on your calculator. And if you do 10 times 10 4 times, then you're going to get 10,000. So that is, exponents is repeated multiplication. So the rule of the decimal point is the number of decimal digits in a decimal is equal to the exponent of 10 in the denominator of the corresponding decimal fraction. So again, this is where 14.89, the 2 tells you how many decimal places, the 5 tells you how many decimal places that we'd need to have here, and the 4 tells how many decimal places in this number. So let's go ahead and practice. We'll take these two fractions and turn them into decimals, and then we will take these two decimals and turn them into fractions. So you can pause the video and try it on your own, and then continue, and I'll give you the answers. Okay, so let's take this first one. 163,079. And if the exponent here is 8, then that means I need 8 decimal places. So counting backwards, that'd be 1, 2, 3, 4, 5, 6. And notice how I have to add 2 more places to get to 8. So this is where we add those zeros in. So it'd be 0.00163079. All right, if we take a look at the next one, it would be 23 and 4 zeros, so 230,000. And the 2 here tells us that we're going to go to the second decimal place and put a decimal point there. And again, we could drop these last 2 zeros, but this is the representation of this fraction. All right, let's take a look at the decimal, 10,000. We write that as a whole number. 10,000 and then 2001. And now we count how many decimal places until we get to a whole number. So it'd be 1, 2, 3, 4. So this would be written as 10 to the 4th power. Okay, and the last one is if we actually could start this backwards. Let's find out how many place values there are here first. And if you count them, you get to 15. So check my counting, but you should get 10 to the 15th power. Now again, we don't need all these leading zeros if we're going to write this as a whole number, so we just start with the 7. 7, 1, 0, 0, 8, 0, 0, 0. So here is how we could write this. Now you might be saying, how can we can get rid of these if this is a decimal. These are kind of some extra zeros that we don't need. And you're right, we can use a cancellation law and cancel these 3 zeros, but that means we need to take 3 place values out of here. So if you saw that and you ended up writing, it should be a 0, 71,008 over 10 to the 12th power, then this would be equivalent, and you'll see on the next slide as to why. All right, so let's answer that question. Why is a decimal representation in this form the same as a decimal representation in this form? So recall that this is 58,900 over 10 to the 4th power is representing our first decimal. So that if we flip it around, let's go ahead and take it to the second decimal. Well, we have to do some cancellation. So this would be 589 times 10 to the 2nd power, or 100. And we can split this up into 10 to the 2nd power times 10 to the 2nd power. Do you see our constant? Our constant is 10 to the 2nd power, or 100. So we can actually cancel those out, and we are left with 589 over 10 to the 2nd power, which is 589 hundredths. So now this is where we've kept this equal the whole way through, so that means that this representation of the point on the number line is the same as this representation of the point on the number line. All right, so let's go ahead. So basically it's adding or deleting zeros to the right end of a decimal point does not change the decimal, as we have proven. So it doesn't matter if we have these extra zeros, because it ends up being the same point on the number line. It's just the partitions are different. So let's go ahead and practice this with this number. I'll go ahead and give you a start, but I'd like you to try this on your own. So here is your head start, and you can work it backwards. So 12 and 7/10 is the same as 127 over 10. So how are we going to get to 12 and 7/10,000ths? Go ahead and try that, and then continue the video and we'll work through it. All right, so if we look at this, we want 4 decimal places, and since we've already got 110 here, what can I multiply by to get 10 to the 4th power? Well, it'd be 10 to the 3rd power. Which means if I'm going to multiply by 10 to the 3rd power there, I have to multiply by 10 to the 3rd power here. So this would be 127 times 10 to the 3rd power, so that I have 10 times 10 to the 3rd power here. So this is our using our equivalent fraction theorem. All right, well, what does that mean if I write this in standard form? Well, it'd be 127 and 3 zeros over 10 to the 4th power. And so now when we write this as a decimal, 127 and 3 zeros, our decimal point moves to the 4th decimal digit, and so here we are. We're at our beginning. 7 and 3 zeros, and 7 and 3 zeros, and these are equivalent. All right, some common conversions of fractions to decimals. We'll go ahead and take a look at that in the next video.